Good afternoon, everyone. We now have the pleasure of welcoming Dr. Panthadeep Bhattacharjee, sir, a respected academician in the field of computer science and engineering. Sir's main areas of working include data mining, machine learning, pattern recognition, and intelligence algorithms. He has received recognitions for his excellent research, including a Best Thesis Award at an international conference. Before joining NIT Rourkela, he has served at reputed institutions such as IIIT Guwahati and KIT University. He is also a professional member of ACM and is actively involved in guiding students in research and innovation. It is an honor to have him with us today. May I kindly request Sir to take the stage and share his valuable session with us. Sir, please.
Okay, thanks once again for attending this session. We'll be starting in a short while and carrying on from yesterday's talk. Today we'll be discussing about the unsupervised paradigm of the machine learning domain, which is called the clustering. So yesterday, let us do a brief recap of what we studied in the last class or last session rather. So we studied about your KNN algorithms. We studied about your naive Bayes classifier, and we also studied about the dimensionality reduction basically. So you must have, if you have gone through the notes or whatever like things that you have taken down. So I've already shared these slides. Like those who are interested, you can actually take these slides now later on basically. So let us do a brief recap of what we studied yesterday, based on which we will continue in bits and pieces basically. So when I talk about the clustering algorithms, clustering is it's a big domain. I mean, it's a big clustering verse, you can say. And there are multiple clustering methods. As I'm told in today's session, we'll have roughly around 1 to 1.5 hours. So I'm supposed to complete within, say, around 70 to 90 minutes time, basically. So we have to go a bit fast. So towards the end of the last lecture, what we saw was that we ended with the dimensionality reduction towards the end of the last session. And we also had, you can say, something called the eigenequation. So in eigenequation, what we saw was that you take a transformation matrix. So where the transformation matrix is coming, I'll come to the slides later on, just around couple of minutes time from now. So we had a transformation matrix called A. We frame the eigenequation, and then we start with the eigenvalues and the eigenvectors. So what is an eigenvalue? So eigenvalue is the scale, So you have says length of this mic rather, what is the magnitude of that vector basically. And what is an eigenvector? If anybody remembers, it's nothing but a pointer towards the transformation matrix. And what is a transformation matrix? It's a representation of a function or a mapping from a certain vector space to another vector space. So mapping, like as you all know, the basic concept of function, we have a certain value in the domain and we have a certain value in the codomain. So in our case, the domain is also a vector and the codomain is also a vector basically. And any mapping which represents a vector space can be represented in terms of a transformation matrix as well. Now, the eigenvalues or eigenvectors, you must be wondering that how are we applying to these clustering algorithms. So today we will discuss primarily 3 clustering algorithms. One is all of you are familiar with, which is called the k-means method. Because to talk about clustering and not to talk about k-means, it's a bit of an injustice to the clustering domain itself. So k-means, I think all of you know, it's a very basic method. It was devised in 1973. So you can say roughly 53 years old, basically. So people who are still using k-means, I mean, I would, you can say strongly suggest that maybe it's time to look beyond k-means basically. Because when we talk about clustering or grouping, mostly people are using the k-means clustering algorithm. But it's a 53-year-old method and there are lots of disadvantages. There are lots of advantages as well, but there are issues with k-means which we'll discuss in course of our presentation. The second method that we will talk about, it's a very, very robust clustering scheme which is known as the DB scan. Okay, DB scan, density based clustering method. And we will exactly try to find out that where K-means has gone wrong and where DB scan has solved those problems, basically. There are certain things K-means always does it, but there are certain things which K-means is not able to do it. There are certain issues, some serious disadvantages are there for K-means, and where DB scan is actually going right or solving some of those problems. But again, DB scan is the first density-based clustering method which was proposed in the year 1996. So it's around 30 years old as well, basically. So all these methods that we'll be talking about, these are very obsolete sort of, so like standard conventional state of the art. But so we have done an exhaustive survey of the density-based methods. I was a part of it. I was leading it basically. And we studied almost all the density-based methods for a period of 23 years. It's not that like we studied for 23 years, but we took the algorithms which span from 1996 till 2019 when we completed the last survey, basically. So that's the exhaustive study that we did. I was a part of it, basically. And we found out that we are moving from DB scan to a very, very robust density-based methods come to 2025, 2024, 2026, anything after 2020, basically, which we'll discuss part of that as well. And the last clustering method that we'll discuss today, it is called the spectral clustering algorithm, which has a strong resemblance to the concept that we studied towards the end of last lecture. So we ended with eigenvalues, eigenvectors. We ended with dimensionality reduction. We will see that how those things are applied in your spectral clustering algorithm, which is again a graph-based clustering method, basically. So today we will see three clustering methods primarily. One is K-means, one is DB scan, and the third is your spectral clustering method. And spectral has a very strong resemblance towards the concepts that we covered in our yesterday's lecture. Your eigenvalues and eigenvectors, dimensionality reduction and all of that. So when we go to spectral, that I will take it as my final clustering method, but I will start with K-means now. To see this, let us again try to understand the concepts here, this title itself, before we go into the details. Everybody is familiar with these terms. Learning is something that I have already explained yesterday, or I think most of us know it. Algorithms, I don't think it needs any further description. And clustering, even if you are not aware of, at least rough idea that you have is that it's a grouping kind of a thing. It's a group of nodes, group of individuals, group of entities, group of objects, anything. But there is a new term that has come into the horizon, which is called unsupervised, basically. So let us start with our usual mode of discussion, that is discussion through explanation, basically. Okay. Now, what is the exact idea of unsupervised? So you have learned about the supervised learning. We know about the reinforcement learning. We know about the semi-supervised as well, but this is something called unsupervised actually. Okay. Unsupervised means, just try to understand, because I don't know whether you will get an opportunity to learn this concept at this level of depth basically. So make the most use of this 1 hour session. What do you mean when you call supervised? I think most of you will answer that, sir, it has a class level. Data has class levels, that's why you call it supervised. Data doesn't have class level, that's why you call it unsupervised. But try to go one step beneath and try to find out the literal meaning of this word and match with this concept that we are using. So what if there is a class level? Why are we supposed to call it supervised? How is class level having anything to do with supervision? These are the questions that you need to ask yourself, right? Again, I'm not trying to go too technical, because if I go to hardcore mathematics, it might be very difficult for a lot of you to judge, basically. So what, there is a class level. Why should we call it supervised? So I can say that it's unsupervised as well, basically. The reason we call it supervised is that it acts like a teacher, actually. It acts like a supervisor. When you have the training data, the input samples, you are mapping with a certain ground truth which is already there. Those who are working in ML models or ML domain, those who have had any experience of training a model, till the time your matching with the ground truth happens, you again keep on going back and keep on coming forward. That's what we do. What's the concept of training? I mean, those who are working in ML, basically. What's the concept of training? We fix the parameters. We train the model, we fix the parameters. Why? To minimize the loss function. And from where the loss is coming? It's the difference between the observed and the ground truth. What is that ground truth? That is nothing but the class level. So if you remove the class levels out of the equation, you don't have the ground truth. And if you don't have the ground truth, you don't have a supervisor, you don't have a teacher. Suppose I'm working under somebody with my PhD guide and I'm not able to meet his expectations. Till the time I'm not able to meet his expectations, he will keep on guiding me. He will keep on punishing me. He will keep on lecturing me. So if you remove that out of the equation, it becomes an unsupervised learning where I'm not under anything on top of me. I'm by myself. But supervised machine learning like linear regression, logistic regression, KNN, decision tree, SVM. I think you have had a session for SVM this morning perhaps. I think Professor Prasenjit actually took it. These all belong to the class of supervised algorithms because there is a teacher ahead. A teacher is actually guiding you that unless and until you reach my expectations, your training is continuing. That's why it's called supervised. Not that mere class level is there. So what, there is a class level. If I'm not going to use it, I'm not going to call it a supervised method. I hope the concept is clear, everybody. It's a basic layman's concept, nothing technical about it. And I think it's very important to understand these kind of concepts before you go into the formulation and the mathematics part of it. Now, why do you call it unsupervised? That means something we are sure that there is no teacher ahead. There is no guide ahead, there is no supervisor ahead. That means the concept of training is somewhat falling flat here. We are not training it exactly. The ML models or the ML algorithms that come under this paradigm of machine learning, we are not training them precisely. The training aspect only happens for those who are under supervised domain of machine learning. Because a teacher or a supervisor is telling you that, look, you have not reached my level, go back and tune your hyperparameters or parameters. Again, come forward. But here, these things are not happening. Right? What is happening is that you are given a raw pieces of data without any class levels. I think now you will be able to relate. Without any class levels, you'll be given raw pieces of data. And the data itself finds its own pattern, basically. It's kind of a pattern recognition kind of a thing. There is nothing called training or finding or tuning any parameters. The parameters should be fixed right at the top. But the data what it will do is that those raw pieces of data will find a pattern by themselves without any supervision happening. And that pattern recognition or pattern identification is called clustering. Because clustering is nothing but, I know it's a group of points, it's an amalgamation of a set of data objects, but eventually it's also a pattern, right? For example, what's the pattern? So if I say this is a cluster, this is a cluster, this is a cluster, roughly you can say that these are convex shaped clusters. What is a convex shape, first of all? Convex means angle between any two straight lines, it's less than 180 degrees. This kind of things, this is convex. If I have this kind of things, this is concave, more than 180. So roughly I can say, I can't say these are ellipsoidal or circular exactly, but somehow people are sitting in round tables. So I can say these are convex shaped groups. And K-means is only able to pick those convex shaped clusters. K-means is not able to pick any elongated shaped clusters. For example, this group, it's a sickle shaped kind of, somewhat rounded. 3 individuals are sitting, it's this shaped, just this kind of. It's not a complete circle. It's just this shaped. It's an arbitrary shaped. For example, if I have a straight line, it's an elongated cluster, but it's a cluster, right? It's a very heavily compact dense points. It's a cluster. It's a straight line. It's a straight cluster or an elongated cluster. For example, you have an S-shaped clusters. People are here, 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 here. As we see in Republic Day or in our national celebrations, do dance competition and all of that, people form the shapes arbitrarily, basically. K-means is not able to pick those clusters. K-means is only able to pick circular shaped clusters, convex shaped clusters, which are roughly ellipsoidal sort of. So just think that if I give you a set of clusters which is arbitrary in shape, then what will you do? Will you still keep using K-means? Perhaps the answer is no. That's where the limitation of K-means lie. You can please note it down. That's the serious disadvantage of K-means. Because whatever I have seen is that whenever people talk about clustering, they start with K-means. But first of all, it's a 50-plus-year-old algorithm. And secondly, it has some serious issues with your outlier picking, noise detection, and finding arbitrary shaped clusters and densities. That's when we move up. And we go to different clustering paradigms. Density-based is one of them. So welcome to today's talk once again. And I think I've given a brief abstract here, basically, before we start with the presentation. So today's topic, we are going to discuss clustering at breadth. We have 3 clustering methods to discuss. One is your K-means, the other is your DB scan, and the third is your spectral. Spectral is going to be the toughest of the lot. For the sake of the audience, I will skip the mathematics to a larger extent. I'll try to explain it so that you are able to grasp it. The slides are already there. You can refer to it later on. So what is clustering? Unsupervised learning. Why unsupervised? I've already explained it. There is no guide as such. There is no teacher. There is no supervision. The patterns find from themselves. Okay. Requires data but no levels. But again, like I said, so what? There are no levels. The thing is that if there are no levels, there is no teacher also. In the supervised, because there are levels, if you don't use these levels, then again it becomes an unsupervised kind of a method. But because there are levels, you have something to look forward to. That, okay, this is where my target is. If I'm not reaching there, I should again come back and train myself. That's where the concept of supervision is coming. Because there is a teacher lying ahead. Here, there is no concept of teacher as such. No levels means there is nothing to look up to. It's a blind journey, basically. You start from here, you just go blind, and whatever you form, you form. There is nothing to look forward to. Whatever you form, you compare with the ground truth. That's it. There's no concept of training as such. So detect patterns, like I said at the beginning of the session. What are patterns actually? Nothing but clusters themselves. Group emails or search results, customer shopping patterns, regions of images. These are some of the applications. Useful when we don't know what you are looking for, very importantly. Very, very important. So, you see, you don't know means what? You don't have any guide as such. You don't have any teacher as such. That means you start from here, you apply the algorithm, you find some patterns, that's it. You don't know whether it's right or wrong, but you are blindly trusting on the algorithm. The trust is there on the model itself that by the time I stop executing my model or my algorithm, I will end up finding some patterns. But whether this is at all the pattern or not, that's a different story altogether. So the basic idea is that group together similar instances, for example, 2D patterns. So today's slide, before we go to the spectral, I will try to keep it as simple as possible. I mean, discussing the mathematics is all fine, but in a 1 hour session to understand the mathematics, it's a very hectic job, especially if you are new to such subjects. So I'll try to base my explanation so that it becomes more pictorial sort of. And my professors also used to tell me that whenever you explain something to others, just imagine that your audience doesn't know about the subject, basically. That's how your explanation should be based. If you assume that they know everything, then your skill of presentation is not tested. Just understand that they don't know anything, and if you are able to make them understand, then that's the real credibility of your presentation. So anyways, I hope I've been able to do justice to it. I don't know, actually, but still. So now you see, this kind of patterns, it's a congregation. It's a congregation. It's a compact set of points. But if you look at this portion, and this portion, the choice is yours. Either you want to put both those elongated, so this is an elongated cluster, by the way, which K-means is usually not able to pick. Why it's not able to pick, we'll discuss it later on. Now, either you put both those things in a single club, or you give two cluster designation to both of this. So this is one cluster, this is one cluster, this is one, and this is one. Right. Now, because you are blinded, you don't have any supervision as such, you don't really know whether it's a correct detection of patterns or not. So, in case you have used those metrics called F1 score, I think most of you have used. Anybody who has not used F1 score, precision, recall, all of you have used, right? 2PR by P plus R. Those are actually classification metrics. They are actually required to judge the robustness of a ML classifier model, which are supervised. In case of clustering, those F1 things are actually not very applicable. They have different ways of judgment, basically. I don't know if somebody has heard of it or not, but I'll tell you a few metrics. Maybe you can note it down. Your first is your normalized mutual information, NMI. I think you have probably known. Your second is your adjusted RAND index, ARI. Third is your RAND index, RI. Then you have the conductance score, only Q. And then you have the accuracy and the modularity maximization, or the modularity. These are the metrics through which you judge that whether your clustering quality is good or not. Mind you, F1 score is used for judging the robustness of a ML model, classifier ML model. That is a supervised algorithm. That is different. You can't apply F1 score here, precision recall here to judge the robustness of a clustering algorithm. That is not a perfect judgment. In order to judge the quality of clusters, that means what I said is that because it's an unsupervised model, so you are actually finding out patterns from blind, from absolutely nothing situation. But are you sure that it is matching the ground truth? Because there is a ground truth. There is a ground truth later on to compare. It's not shown you at the beginning stage, but there is a ground truth to compare. Are you sure that this is actually the clusters what the ground truth is or what the experiment has said? Then when you start comparing, these are the methods that I have said, the metrics, these are the metrics which are used. There's one more which is called the Silhouette score as well. So these methods are applicable to judge the robustness of a clustering algorithm in the unsupervised domain. The F1 score and precision recall, they are for your supervised domain, basically, right? So moving on, group together similar instances. Now you see, the choice is completely yours. Either you want to put this as C1, C2, C3, or you want to do this kind of a things. Because you are blinded, you don't know what is correct actually. If you slightly change the parameters, you might end up getting this configuration, say 2 clusters. If you have slightly different set of parameters, you might end up getting 3 clusters. So what is correct? That's when these metrics that I've told, they are actually helpful. So for example, this is your ground truth, and this is what your algorithm has found out, basically. That's when you use these metrics or whatever measures that I've said to judge what's the accuracy of your model. Say 70%, 80%, 90%, whatever, basically. But it's very different from precision, recall, and all of that. Those are actually going for your confusion matrix kind of a thing. The true positive, true negative, false positive, misclassification, those things. Here there is nothing called classification. It's all about grouping and finding out the cluster memberships. I hope I've been able to explain in some ways, basically, right? So what could be similar? Again, yesterday we had a very long discussion about similarity, right? What is similarity? Are we just trying to say that like the Euclidean distance means pure similarity? The answer was bit no kind of a thing. In this day and age, Euclidean distance is not a straightforward measure of similarity. There are lots of evolved techniques which have come up. But because these are inherently very old, old algorithms, k-means, so by and large we use the distance function itself to find the similarity. One option is small Euclidean distance error. The algorithms that we work on, we don't use Euclidean anymore, actually. Like I have said yesterday also. Clustering results are crucially dependent on the measure of similarity or distance between the points to be clustered. Now, like I said here, if they are grouped within a certain cluster, one thing is sure that any pair of points within this group is highly similar as compared to points between 2 different clusters. Have you understood what I've said? If I'm clubbing, say, these 4 points in this group and these 4 points in this group, one thing is certain that if I pick any pair of points from this group, they are comparatively more similar as compared to if I pick 2 points from 2 different groups. Had this similarity been more, then they would have merged up basically. They would have been a part of same cluster. But because they're in different clusters, that means anything from here and anything from here, it's highly dissimilar. And any 2 things or any pair of things from here, it's more similar as compared to anything from here and anything from here. But who says what's the similarity? Somebody would say that, look, if I had a point here at this boundary position, and I had a point at this boundary position, somebody would say that, look, they are close enough, right? So why not they're a part of the same cluster? Suppose if I say this kind of a situation, suppose this blue circle here, I had 1 point here and 1 point here. So this is a part of this cluster, fine, fair enough. This is a part of this cluster, fine, fair enough. But if you look at the distance between this, aren't they more closer to each other as compared to this and this? Yes or no? But are we putting them within the same group? No. These 2 points are apparently more closer to each other than this and this. But this and this still lie in the same group, but not this and this. Why? Because we can't trust the Euclidean distance. It's not a game of distance anymore. Here we are saying distance, that's all right. It's a 1973 algorithm out of all the reasons. 53 years back. Probably one of the first clustering methods discovered. Right, I think the number of citations that came in says it's crossing around 30,000, I think, of today, basically. So everybody uses it. But what I'm trying to say is that why they are put different? Because if only distance was the measure of proximity or closeness, these two have been under the same club and they would have merged basically. Clusters would have merged. But because we are putting them differently, that means that there is something more to distance as well. Only distance can't be your measure of similarity. That means there is something which is seriously dissimilar between these 2 points as compared to these and any other points within the same group. I hope I've been able to make sense here. Just try to understand. Right? So, now these are the schemes of the clustering. So, K-means is a partitional clustering method. That means groups. Mixture of Gaussian. So, this is not something we'll discuss today. This is something we'll discuss, the spectral. Why do you use the called spectral? The word spectral comes from the word called spectrum, actually. Any idea if anybody can answer, or else I'll take it basically. Why do you use the word called spectral? Yeah, pardon? Bandwidth, yeah, fine, fair enough, accepted. But bandwidth of what? Okay, I mean, fine. So you are our colleagues here. I at times forget that I'm not taking the class basically. So thank you. Spectral is bandwidth, and it's a spectrum of eigenvalues basically. Okay, so please don't take it otherwise. It's a habit kind of a thing actually. But we all are pretty grown-up professionals. So spectral means we are using the eigenvalues here, and the word spectral comes from the word called spectrum, which means a list of eigenvalues, the width of eigenvalues. But how we are using the eigenvalues, it's very interesting, which you will see in the later part of our presentation. Then we have the class of hierarchical algorithms. We have the bottom-up method, the agglomerative. So these are all, these all are clustering algorithms. They have their own set of advantages and disadvantages. Right. The disadvantage of this group of methods, so this is one clustering algorithm, this is one class of clustering algorithms. The disadvantage is that the amount of RAM that is required to store a certain data structure, called dendrogram basically, that is more in case of these hierarchical methods. That's why they are useful in some applications, but not always preferable. Mostly what we do is that, mostly we go by this because of its simplicity, that's all about it. It is not a robust method by any means. K-means is not the most robust method, but only because it's simpler to execute or calculate, mostly people use K-means. Mostly you will find people go for your density based, the second clustering method that we are going to discuss. So it's all about clustering. Now we come to the K-means basically. So I think K-means is known to one and all. I think most of you had probably known what K-means is. So I'd still go through the concepts of K-mean. Yesterday one of our professors, he asked that how do you fix K basically. So we had a problem with K and N, the K nearest neighbor, and we said that the degree of smoothness we compute basically. Where we had a smooth classification, we say that this is where we finalize K. But here, as he already pointed out, I think, sir, probably you pointed out, yeah, the elbow method that we use, right, the elbow method. So what is the elbow method? For the broader benefit of our audience, it's a method which computes the within the cluster sum of squares distance, basically. It's called WCSS. Okay. Okay. So what does this mean is that WCSS, that means whatever mean of a particular cluster is, so suppose this is the centroid of a particular cluster, then all the points are computing their distances with this centroid. Right? I'll come to K-means slightly later, but what is the objective of K-means actually? All the points, all these dots you are seeing, they are actually computing their distances with this designated mean or the centroid. And every distance that is computed, they are actually finding the squares of those distances. Squares. That means this square plus this square plus this square plus this square plus all the distances which are there. The sum of the square of the distances is found with respect to the centroid. Now, a certain value will be there in the along the x-axis, which is your WCSS score, basically. For a certain value of K. So what is K here? K is the number of seed points. K is the number of seed points, initial number of cluster centers that we take, basically. Suppose we start with K equal to 1. We'll find out what is the WCSS score. Then we go to K equal to 2. We'll find out what is the within cluster sum of square scores. Then we go to K equal to 3. We'll actually observe a inflection point, basically. That's called elbow. Why it is called elbow? Because it looks like an elbow, basically. We'll observe an inflection point where your intra-cluster score will probably be ideal at this zone where your inflection actually happens, basically. And this is the value of K we decide. Or else it will be very difficult. What's the value of K? Because based on the value of K, your entire clustering will be decided. What is K initially? So let us look at the algorithm. Pick K random points as cluster centers. But again, there is a catch. Because your choice of K will decide how many number of clusters will be there. But are you sure that many number of clusters will be there? Suppose in this data distribution, so suppose this is the ground truth, basically. And I am going to execute my raw data set in the K-means algorithm. Suppose I pick this as one of my cluster centers and this is one of my cluster centers. Say here, this point, and suppose this point. I will get some clusters, but I will get only 2 clusters basically because I have picked K equal to 2. Okay. But is it really a 2 cluster situation? The answer is a big no. Because by visual estimation, what we are seeing is that 1, 2, 3, 4, and 5. There are 5 clusters. At least it looks like, basically. But if I pick K equal to 2, suppose I don't know this elbow method, and if I pick K equal to 2, every time my algorithm will keep on iterating and it will give 2 clusters only. That means all these points here, they will somehow try to be as close as possible here. Somehow. But it will be a very wrong clustering demonstration, actually. So who has done the mistake? Your choice. Your ground truth says that there are 5 clusters, but actually because the wrong choice that you have made it as K equal to 2, what you have done is that you have made it a 2 cluster kind of a scenario, and unwantingly, points are not belonging to this cluster, but just because of the algorithm or the execution, somehow they are put in this 2 cluster kind of a scenario, which is a very, very wrong cluster demonstration. And the reason for this wrong cluster demonstration is your initial choice. So that means it's imperative, or it's very important rather, that we fix this initial choice right at the start. How do you do it? As Professor mentioned out yesterday, we do it by the elbow method, actually. And how do you execute the elbow method? By a score called WCSS, or within cluster sum of squares. So your vertical axis is your within cluster sum of squares, and as your K increases, you can see that WCSS tends to decrease, basically, right? So it's better that your WCSS is on the lesser side. That means clusters are more compact, basically. Clusters are more compact. So this is your inflection point. From here, you can say somewhat a reduction trend is actually observable. So this value of K, we assign as our initial number of cluster centers. But that you have to do it experimentally. It's an empirical validation, kind of. You don't know what it is. You start with K equal to 1, you start with K equal to 2, you start with K equal to 3, K equal to 4, K equal to 5. From where you start seeing the dip, basically. That's the point you pick. Said, look, I'm going to pick it as, but that purely depends on the data distribution. It's not that there is a particular value of K that will be suitable for all the algorithms, all the variations of K-means, basically. So next what we do, assign the data points to the closest cluster center and change the cluster centers to the average of its assigned points. Now, I think most of you know this, but still I'll be explaining it once. What it is trying to say is that, suppose blindly I have selected very correct cluster centers, blindly. Suppose my guess is right initially. So what I have done is that I have selected, say, C1, C2, C3, say suppose I select this point, C4, and suppose I select this point, it is say C5. Suppose hypothetically I do a very, very correct guess, hypothetically, by luck, for example. Now what happens is, every point in the data set will now individually compare with all these mean points. These are cluster means or cluster centroids, basically. Right? So those who are new to K-means, probably you can understand from this. What I'm trying to say is that you select K equal to 5. So now you have K equal to 5. Okay. And what you do is, now you start processing every point in the data set, every point. You have same number of points you have, you start processing from p equal to 1, p1, right? You take a certain point, you compute the distances, it's a Euclidean distance, you compute the distances with all these randomly selected cluster centers, right? You compute the distance with this, you compute the distance with this, you compute the distance with this, and with this, basically. So which is the closest? Apparently this appears to be the closest. So this particular point will get a cluster membership which is headed by the point C5. I'm repeating once again, this particular point will become a part of a cluster which is headed by the point, or which is led by the point, or which is the mean of that cluster is C5. That means this point is now already assigned a certain cluster membership. What do you mean when I say assigned a certain cluster membership? That means it has gone to a certain cluster. That means the cluster whose mean point is C5, that cluster will now consume this particular point called P1. Now you come to point P2. Say again, suppose this point is P2. It has computed its distance with this, distance with this, distance with this, distance with this, and distance with this. Which is the closest? Again, this looks to be the closest. So this particular point P2 will again go to a cluster whose centroid is C5. Come to P3. Again, compute the distance with all those mean points, or mean and centroid are the same thing. Compute the distances, this with this, with this, with this, with this. Again, this appears to be the closest. So don't you think that all the points which are lying within this horizon, every time I calculate, they will be closest to this as compared to the other means? Whatever the points are within this zone, they will always be closest to this as compared to rest of the other means. So they are bound to be a part of this group, or this complex, compact region rather. They were there, but we were not picking it up. Our job is to pick it up through k-means. Just try to understand. This is already there. But what we are given is that in a text file or a CSV file or in an Excel sheet, we'll be just given the data set. And we'll be asked to run through these k-means. Whenever the k-means produces the clusters, are we getting the same picture what my actual data distribution is? That's when the accuracy thing comes into the picture. We are not training it here. We are giving into the algorithm input data set, finding out the clusters, then comparing with the ground truth. That's when the accuracy matrices that I told a couple of minutes ago, those are now applicable actually. Fine. So if you come to this, anything from here, it will obviously be closer to this as compared to rest of the other means. So every point that lies within this horizon, it's going to be a part of this cluster, because they are closest to this mean as compared to rest of the other means. Now come to this. So the problem is with these border points basically. So for example, there is a tie. Either this or this. Then randomly we decide it. Either you go to this cluster or to this cluster. The usual way to decide is that take one which is a lesser index. For example, if this is C3 and C5, and suppose a point here, it's as equidistant from this mean as well as this mean. You can attach it to cluster whose centroid is C3 or C5, either ways, but eventually take the lesser index. So you see all the points, whatever they are basically, the ones which they are closer to, but a comparison is required. By eye estimation, see, this is visible to you because you are seeing this diagram. Algorithm is not knowing this diagram. It will compute the Euclidean distances and find out which of the means that every point is closer to. That's what the first point is. Assign data points to closest cluster center, basically. Got this point? So your one iteration, first step of the first iteration is over. Then what do? Come to the second step. Change the cluster center to the average of the assigned points. Now what happens? Now C1, C2, C3, C4, C5, these are my initial assumption. By luck, I thought that maybe these 5 will be the cluster centers. If they are or if they aren't, I don't know. I assumed it initially. I applied the elbow method. I found out that k equal to 5 appears to be a good enough value of k. And then I thought that, look, let me pick 5 points from this data set. The choice of 5 points is up to you. And I picked the 5 points and I got a configuration something like this. Now, the second step says is that this mean might shift. Come to cluster 5. Compute the mean of this, all the set of points which are there in cluster 5. Right? Can somebody put out? Now what is happening is that this mean is now again freshly computed. How? Whatever points are assigned to this cluster, their x coordinates, y coordinates mean are taken, z coordinates mean are taken, a fresh mean is actually found out, and this mean either remains same or it might shift as well. Similarly, again the mean of this cluster is again freshly computed, mean of this cluster is freshly computed, mean of this cluster is freshly computed, mean of this cluster is again freshly computed. And then what we do, we execute the WCSS once again, within cluster sum of squares. We have a certain value. Then again we repeat these steps 1 and 2. Again we come to point 1, again we compare with this freshly computed means. So if there is not a significant shift in the mean, always it will come to this cluster only. Yes or no? Because it's maybe there is a slight tilt in this mean. Maybe this was the point before in the first iteration. Now this mean has been just a point which is very near to this. But all the points still will be closer to this as compared to rest of the other means. Yes or no? I hope you have understood. Shall I repeat it once again? So this point which was a part of this cluster in the first iteration is going to retain its same cluster membership now also, because there is not a significant shift in the mean. And in some cases the mean doesn't change at all. Similarly, all the points which were a part of this cluster, they more or less 95% of them, they remain a part of the same cluster itself. Maybe very few of them, they migrate. Very few of them. Suppose your mean shifts drastically, then you see a bit of a migration. Because points which are the border points which are here, they have now, they are probably more closer to something which is nearer to them as compared to this mean. Only then the shift happens. Or else most of them, they retain their cluster membership. Most of them. And after the second iteration, I again compute the WCSS. So you must be wondering that how long we keep repeating this process. Again come for the third iteration, again freshly compute the distances, compare, assign the cluster membership, again compute the mean. How long we are going to do it? There has to be a convergence point, right? So we continue this process till the time no points change their clusters. By the end of third or fourth iteration, more or less we are sure that what is the membership of a certain point to a certain cluster. So till the time we reach a point where the points don't change their cluster membership, they are not moving. Whatever is there, they are in that cluster itself for a significant period of time. They are not moving basically. That's when we stop the iteration and say that, look, we have obtained our clusters. Is that clear? At least 60% maybe you have understood basically. So stop when no points assignments change. Right? So moving on, an iterative clustering algorithm. Iterative means we repeat it pass by pass. Pick k random points. See, these are very important lines. Pick k random points. It hasn't said that what points you are going to pick. It's very random. This I said by luck if I'm picking, but if you pick a very wrong distribution of points, for example, if you pick 5 points from here, here, you are going to get very wrong representation of clusters. Because this itself is a cluster, but just because you have picked wrong set of 5 points, unwantingly they will be a part of a certain cluster, but that will not be their correct representation basically. So this again, picking of these points, again, it's a bit of an intuition sort of a thing basically, right? So assign data points to the closest cluster centers, change the cluster center to the average of its assigned points, stop when there are no assignments. And we have more or less this kind of partitions happening. These are the partitions which are happening. But again, you see that if I say this is a partition, this is a partition, this is a partition, this is a partition, but the blue zones are your actual representation. The black partitions, what k-means is giving you. It's not accurate, as it's obvious from the diagram. Maybe you are picking this like the way it is, this particular cluster, but here you see k-means is picking this one segment as your complete cluster, but your actual ground truth is there are 2 clusters here. That's where the accuracy starts shifting. It's the comparison of accuracy, right? So pick k random points as cluster means shown for k equal to 2, and you can execute in your Jupyter notebook in your Python code as well. You will vary the parameters, you will see different distributions actually coming up. The codes are available everywhere, It's a very basic algorithm. Assign the data points to the closest cluster center. So this is what it is that we said. Change the cluster center to the average of the assigned points. Repeat until the convergence happen. So whatever we explained just few minutes ago, exactly what this slide is actually saying. So you see there are somewhat bit of misclassification happening. Not classification is not the right word to use. Maybe some points which the ground truth says should have been a part of red cluster, they might belong to the blue cluster. That's why we find the accuracies. The metrics that I've said, NMI or ARI or Silhouette score, etc. We are using this just because of this. It might not be exactly matching with the ground truth, but by and large it will be matching. By and large, maybe 80%, 90%. So this is all about it. What is the time complexity? The time complexity is order of kn, where n is the total number of data points and k is the number of cluster centers, basically. And change the cluster center to the average of its assigned points, its order of n. So what properties should a distance measure have? They are symmetric, positivity and self-similarity, and triangle inequality. This is all about k-means, but this is the maths basically. This is the maths behind k-means. This actually is the equivalence of the WCSS score. Our objective is to minimize the WCSS score, or within cluster sum of squares. If you see the inner sum, it is belonging to a particular cluster, all the points, and the outer sum is the number of cluster centers, or number of clusters rather, actually. So what are the problems with k-means? What are the issues with k-means now? The issue is, if you look at these clusters actually, you see, by and large, if you draw a shape kind of, it's more or less a convex kind of a representation. I won't say exact circle or exact ellipse or exact globular or spherical sort of, but somehow you see there is a closed loop kind of, roundabout closed loop. Similarly for this, similarly for this, similarly for this. But this is a very perfect case of k-means. I mean, these are the clusters which k-means will be able to pick it up, because these are the convex shaped clusters, right? But what about this cluster? For example, this one. This is also a cluster, right? This is also a group of points. So k-means actually suffers from this problem. It is not able to pick this kind of clusters. For example, in a remote part of my data space, there is a very compact group of points are there, say 50 to 100 points are there. But they are not circular in shape, not globular in shape, they are somewhat irregular sort of. K-means is not able to pick them up. K-means will pick this up. Somehow it will pick this up, but it's not going to pick this up, basically. That's what we do, is that we migrate to a different clustering paradigm called, these are the examples of k-means. K-means are getting stuck. It's a very outlier sensitive algorithm. So if you have more number of outliers, again k-means suffers. And k-means is not able to properly cluster this. So if you see here, this is a cluster, perhaps. This is one more congregation. It is not able to pick this kind of things. It might be able to pick this, but it will not be able to pick this. That's what the problem of k-means is. So please try to remember the disadvantages of k-means are, although it's a very efficient clustering method, one is its sensitivity to outliers. More the number of outliers. So what are outliers, by the way? So outliers are the data points which are not a part of the clusters. They deviate from the pattern, actually. So there is a difference between outliers and noises. So these terms are used very interchangeably, but noises and outliers are not the same. Noise is a misclassification error, and outliers are a serious deviation from the error, from the clusters, from the pattern rather. That's the difference between the noise and the outlier. So next, what do you do? Because k-means is, so again, like I said, this is again a elongated cluster, and k-means might not be able to pick it up. It might return some clusters, but it will not be what the ground truth says, basically. Okay. So in order to remove this disadvantage, so today we are supposed to stop at 4:30. I am told. Am I right? 4:30, right? Okay. So because there is this problem of k-means, what do? We go to a new class of clustering algorithms, which is called density-based clustering algorithms and graph-based clustering algorithms, primarily density-based. So it was actually propounded in the year 1996 in the University of Munich in Germany by Easters, Michael Sanders and his colleagues basically. And it somehow removes the disadvantages of k-means, but not totally. There are issues with this also, but all the density based, I mean, this also has around 25,000 plus citations now. I think it has crossed maybe 30, close to 30. Not like k-means because it's around 30 years old, this method. Okay. So every density based method will take dbscan as its citation, actually. So the evolved density based methods, which are being proposed now recently, say 2020, 2019, 2024, 25, they are far more robust than what this dbscan is. dbscan is the first density based clustering method, basically. So distance based clustering and its limitations, like I said, when you use Euclidean distances, there are issues. Hard to find clusters with irregular shapes, hard to specify the number of clusters, and some points are in between clusters like outliers or background noise. Now you see, for example, you have a biological data. Maybe your infections or microbes might have this kind of a structure. When you do the diagnosis they might have this kind of a structure. But if you want to use k-means for this purpose, k-means will not be able to succeed. K-means might be able to pick this cluster, but k-means will fail to pick this congregation of points. Because when I say clusters, don't stay in this notion that only circular group of points or globular group of points are clusters. No, this is also a cluster. It's a kind of an S-shaped cluster, basically. This is also a cluster, an elongated shaped cluster. This is also a cluster. Am I going somewhere wrong? Okay. Can just call someone just to be here actually for this one. Okay, so I think I don't think we'll have time to do spectral. If it's 4:30, maybe you can stop with dbscan itself. Is that fine? Okay, so can I make this the last? Or we want to know spectral? Because spectral clustering will take a bit of time. Till 4:30. Okay. 4:35. 4:40. I don't know. I don't have any problems. Okay. So you see, these regions are also your groups, basically. Okay. Now, even this region is a group. So any compact space in the data set becomes a part of a cluster. But there are these methods, these k-means like methods, they are not able to pick this. That's what I've been mentioning right throughout. But you can't really ignore them, right? So you have say 5 or 6 or 7 clusters here. You apply k-means, it will pick this and it will partially pick some of them, maybe not all of them, which is again a wrong representation. So that's when we take help of this density-based method, density. So why do we use the term called density? Like we said yesterday in our session, in our lecture session, that density means the congregation or the compactness, basically. The more you have the crowd around, on and around a certain region, that area is called as highly dense, basically. Now, because of I'll discuss how dbscan works, because of the property of density-based methods, anything which is by and large dense, it will able to get picked up as a cluster, okay? So new concept, cluster is a probability density peak. But how to define the PDF in multidimensional space? For example, if you look the similarity between these two diagrams, you see when we come to this region, so suppose you are scanning from left to right, actually. When you are part of this region, there is a certain peak. That means your density or your compactness or your heaviness within this region is significantly higher. Then you come to this part. You see there is lot of blank space or a sparsity. You observe a spike down, actually. right? When you apply a certain function, okay. When you apply a certain function, it will actually give you a okay, let's continue. So when I come to this region, you see the sparsity is more. That means the compactness of the points is not as much as it was in this region. So you observe a sharp spike down actually. That means what I'm trying to say is that there is a certain probability function which takes arguments based on your density. Say, suppose it take a set of data points as x. So whenever you come to this particular region, your function return point will be, or return value will be very less. Again, as you go to this spot, you see again the points are starting to fill up basically. The regions are again getting heavier. Again, you observe a spike, right? And then there is a very long gap of sparsity. That means it's a relatively empty region. So you observe this region basically. The spike is a bit more prominent here. And then when you enter this, it's probably the most compact region or the densest region. And as you approach towards the middle part, basically, this region, you see the spikes are far, far greater as compared to any of the spikes in the past. So if somebody says that, look, instead of a clustering diagram, I give you a plot of a probability density function, you will be able to somehow at least find out that what your clusters exactly should be like. And that's how we find the accuracy. For example, suppose this is your ground truth, and if I apply a certain algorithm, say for example k-means, I might get something like this or maybe like this. And when I compare these two distributions, they are not identical, so I can say k-means is less accurate as compared to a method like dbscan, which might give me something like this. Right? So instead of just looking at the visual demonstration, if you plot a probability density function, you will still get an idea that how your clusters actually look like, basically, which say some of the partitional methods are not able to pick. So that's how it's like we pick up the denseness of the clusters. So here also we see, I mean, for every your diagram, these peaks or these points, they are actually representative. But then again, it depends from method to method. Suppose your method is picking up a certain set of clusters, your distribution is giving something, say, slightly different. So you can say that your method is not exactly appropriate. Your distribution has to be pretty correct, but your methods will vary. So maybe out of all of this, probably this gives the most pronounced results. So your distribution is also more or less looking like an appropriate one, basically. So now we come to the DB scan. It's a very interesting algorithm, basically. And you see how it's different from k-means. It's a completely different brand of algorithm, basically. So let us see what are the problems of k-means. K-means is outlier sensitive, and k-means it's not able to pick arbitrary shaped clusters. These are the two disadvantages that we studied with k-means. So our first priority is to make a certain clustering algorithm which is robust to outliers. That means, so what are outliers? These are actually outliers, these points. And whatever points that are lying within this group, they are actually clusters. So that's the difference. Outliers are not getting a cluster membership. They are not a part of any group. They are different. They are deviating from the patterns. For example, I am an outlier in this room. So all of you are clusters. So you are in compact patterns. You are sitting in groups. I am sitting far apart, or maybe he is there. So we both are a small cluster, basically. That's the best way to actually explain, right? So let us see how we start with DB scan. DB scan has few parameters, first of all, or hyperparameters, should I say, the external parameters. First of all is your radius, which is known as epsilon, right? Your second is your mean points. So let us say mean points. I'll explain what it means, MINPTS. And your third is, so your epsilon is your first hyperparameter, your mean points is your second hyperparameter, and third is your, say, I think there are two basically, epsilon and mean points. So let us start with DB scan first of all. Every point in this data space, so you have n number of data points. We start with n number of data points. Every point in this data space have two categories. Either it's dense or it's not dense. Fine. Let me repeat it once again. Every point in this data space has two categories. Either it's dense or it's not dense. The other term that we use for dense is core. Either it's core or it's non-core. Same thing. Either it's dense or it's non-dense. Either it's core or it's non-core. Same thing. Dense means core, non-dense means non-core. So how do you find out a certain point is core or a non-core? How do we find out, first of all? So what we do is, let's try to understand. I pick a certain point and I draw a certain radius. Say suppose the value of that radius is 5. Arbitrary selection, say 5 is the length of that radius. I draw a radius of length 5 and I construct a circle around this radius. Clear? Very obvious. Very simple. I pick any point. This, anything I pick. Arbitrary selection. And I draw a radius based on the epsilon value that I select. Say epsilon equal to 5. Now I construct a circle based on this radius. And then I will find out in this region how many points I am accommodating. Is it clear, everybody? I take a point, I draw the radius, I construct a circle over this radius, and I find out how many points I am getting within this neighborhood or within this circle rather. If those number of points are crossing my second hyperparameter, which is mean points, crossing greater than equal to, then it becomes a core point. But if it's less than that, the mean points hyperparameter value, then it becomes a non-core point. Right? So let me explain it here through diagram. So I pick a certain point here and suppose the radius is say 10 cm, 10 centimeter or say 10 length units, whatever. So now what I do, I draw a radius of length 10, say suppose this is 10, and I construct this entire circle. This region is also known as epsilon neighborhood of this particular point, say x. So this is point, say x. And how many points are there within its neighborhood, including itself? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Or rather say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, including itself. Right? So n epsilon will be 11. Now, this is my second hyperparameter, which I have fixed it to 5. Right. So I had two hyperparameters. One is your epsilon and other is your mean points. Epsilon is the length of the radius and mean points is a core point formation threshold, basically. So because this is greater than 5, X becomes a dense point. That means the physical significance is that the crowd within my neighborhood is very heavy. That means if I draw a probability density function, I will get a peak. Right? That's what we explained in the previous. Say suppose this point, for example, this point. You see, if you draw a certain epsilon here and you try to find out how many points are within this neighborhood, it's very heavy. Very, very heavy, very heavily pegged. On the contrary, if you pick a point here, for example, if you pick a point here and you draw a circle, you see this is a bit sparse area kind of, basically. So as compared to this point and this point, which looks denser? This looks denser. This is heavily packed. This is dense. This is core. On the contrary, based on whatever values that I get, this might be core as well, but based on eye estimation, what I find is that this is a non-core point or a non-dense point, basically. So now every point, so now suppose I pick this point, what I do is that I draw a radius of 10 and I draw a circle, kind of, here. Somewhat like this. Again, I find out the number of points within this region, epsilon neighborhood of this particular point, let it be called as y. If the number of points are crossing this particular threshold of 5, then this also becomes a core point. But if the number of points are below this threshold of 5, it's called a non-core point. For example, a point like this. For example, this. So what is the number of points that are within this region? Only 2. And including itself, it's 3. Is it more than 5 or less than 5? It's less than 5. So this is a non-dense point or a non-core point. So there will be, for every point, there will be circle, 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 or say region, 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 region. There will be a lot of overlapping regions, basically. But those are not clusters. Those are not clusters. They are just to identify whether a particular point is a core point or a non-core point. How do you identify? Pick a point, draw a radius, draw the circle, find out how many points are within that circle. If it crosses this threshold, this is externally set user input. If it crosses that threshold, this becomes a dense point or a core point, or else it's a non-core point. Till now, if you have any doubts, you can please ask. This is very important. We still haven't gone to the clustering part. Maybe it will already be 4:30 by the time I end up explanation of this. We might not be able to cover spectral because now the clustering will start and it's a bit complex, basically. I hope everybody is understood till now. We are just doing a classification of core and non-core. Pick an arbitrary point, draw a radius, draw the circle around this, see how many points are within that circle. If it crosses this already user defined threshold of 5, or say whatever the number is, you are a core point, not the other points. You are a core point, not the points within your circle. They are just a adding up entity kind of. Say I pick a point, say I pick myself, I draw the radius, nobody is around me. I set a threshold of 5, I need 5 people or more than 5 people to classify myself as a core point. But I'm not getting it, so I'm a non-core point. So for example, somebody sitting at that corner, if he draws a radius, draws the circle around him, he's at least getting 10 other people around. So it's crossing 5. So he is a core point. You are not the core point. You can be a core point if you satisfy these criterions. That will process it later on, point to point. Your processing will be done when your time comes. But at the meantime, he is a core point. Then I go to say, sir is sitting here. I draw the radius, maybe 3 people are sitting here. So you are still not satisfying this criteria of 5. It's less than 5. So you are also a non-core point. Right? There are issues with that. I will say why. Suppose I say threshold is 500. Anybody which is 499 will be a non-core point. Anybody whose neighborhood has 499 points, unfortunately, will be a non-core point. And anybody who is 501 points, unfortunately, will be a core point. And that's the bad thing about it, because even 499 is very heavily pegged. Here we are giving 5, 6, 7 small examples. But if we go to larger numbers, 499 is also heavily packed. But just because the algorithm says that if you are less than that number, you are an on-core point. We have to follow this. There is no way. That's the disadvantage. It's a hard density problem. These disadvantages are solved by present-day density-based clustering methods. But let us stick to it for the time being. Now, what happens is, say, this is core, this is core, this is core, this is non-core, this is non-core, this is non-core. And every point is now it's either a core or a non-core. Right? So what we have is graph of core points and density reachable peripherals points are now identified. So just try to pay more attention. It's a bit of a complex part, and I think probably we'll have to stop at DB scan. It will already be 4:30. What is my estimation is. I'll have to take help of this whiteboard software to explain this part. It's not that simple, actually. So yesterday we had this basically. Yeah. Then I'll come to this slide, but this explanation is very much required. So what is the scenario now? So let us say these points are there. And I pick a particular point. It's visible to all, right? I draw a radius. Say this radius is epsilon and its value is, say whatever the value is, maybe 10 or 5 or whatever. Whatever, let us keep it epsilon itself. Some length is there, that's not the main thing. Now what I do, I draw a radius and I draw a circle of radius epsilon. These points are now counted. These points are now counted. So I have this an epsilon. If it's greater than the number of points here, say mean points, then it's a core point, or else it's a non-core point. This is all what we discussed now. Now, imagine we are doing it for every other point. This is the most complex part, so try to pay a bit of an attention. Now we move to, say, suppose this point. Okay, what we do? We again draw the radius. We again draw this kind of a circle. And again we find out what is there, how many points are there within this region, basically. If it crosses this threshold, this becomes a core point, or else it's a non-core point. Now I come to say this. Again I draw this. Again I draw this circle. Again I count the number of points within this region. So these all are epsilon neighborhoods of that particular point, right? So this is your x, so this is your x. Your x can be your x1, x2, x3, whatever. Again, this is, say, either core or non-core. So suppose this is non-core now. That means it doesn't have enough of points within its neighborhood. Now what my algorithm says is, if any two points are directly density reachable. What is directly density reachable? There are two things. One is directly density reachable, other is indirectly density reachable. That means any two points lying within the same epsilon neighborhood. That means this lies in the epsilon neighborhood of this, and this lies in the epsilon neighborhood of this. That means whenever I took this point as my point of contention, I drew the circle. This is the region of this particular point, right? Whenever I took this point as my processing, this is the circle for this particular point. But this also came in this one's neighborhood, right? Whenever I draw the circle of this particular point, this came in this neighborhood, right? And whenever I draw the circle of this particular point, this came in this neighborhood. That means they are now directly density reachable. That means within the neighborhood of this particular point, I have this particular point. That means within the same circle, I am actually able to reach that point. And it's a core point also. Two conditions. First of all, it has to be a core point. Secondly, it has to lie within the same periphery or same boundary or the same neighborhood of this particular point. Then this is directly density reachable. Now, what about this and this? I take this point, draw the radius, draw the circle, and is this lying within this neighborhood? Possibly yes. So this is directly density reachable. This point, is this lying within, you see, the circle ends here, the point is within the circle for this point, basically. So this is also directly density reachable for this. Now, what about this and this? That's the game changer, actually. You see, take this point, draw the radius, draw the circle. These points are within this circle. This is a core point, this is a core point, and unfortunately, this is a non-core point. Non-core point will process later on. These two are designated core points, including the center point itself. So, because they are within the neighborhood of this is directly density reachable from this, and this is directly density reachable for this. Fair enough, done. What about this point? This and this. Because although this is a core point, but it lies outside the region of this. You see, the region of influence of this point has ended here. Draw the radius, draw the circle, its neighborhood influence has ended here. But this point is outside the region of influence or neighborhood of this one. Neighborhood is the term that we use technically. This point is outside the neighborhood of this point. But it's also core point, and it's directly density reachable from this, but not this. So such points are called indirectly density reachable. That means it's reachable, but through a third point. It's reachable, but through a third point or a fourth point. So how to reach here from here? From here you go here, from here you come here. So this is indirectly density reachable with respect to this point. This is directly with respect to this, but indirectly with respect to this. What about this? This is again outside the neighborhood of this. Am I clear? Again outside the neighborhood, but it's a core point. Now I have to see, is there a path existing through some of the intermediate points through this from this? If then it's an indirectly density reachable. Clear? Just let me know if this step is clear or not. Our clustering will start now. Concept of density, non-density is clear. Take a point, draw the radius, draw the circle. If the crowd is more, crossing a threshold, you are dense or as non-dense. Every point will be classified as dense or non-dense. What is directly density reachable? Any two core points within the same neighborhood are directly density reachable. What is indirectly density reachable? Any point which is core but not within the neighborhood, but I can reach them through a third point or a fourth point. That is indirectly density reachable. But it has to be a core point. Non-core will come later on. Now that we have understood the concept of direct density reachability and indirect density reachability, let us go to the graph once again. If two points are directly density reachable, that means they are lying within the same neighborhood. By default, they are a part of the same cluster. So let us now slightly alter the scenario. These circles are not clusters, by the way. They are just a region of influence, neighborhood basically. They are not clusters. Now the cluster formation will start. If two core points, say core point P1 and core point P2, if they are core first of all, and they are within the same region of influence or neighborhood, that means they are directly density reachable, then by default they are a part of the same cluster. They are a part of the same cluster. Now, all these points, if they are directly density reachable from P1, they are now part of the same cluster by default. There is no rocket science behind that. Within the same neighborhood, it's a core point. That means this concept. These points are now, these points are by default, they're a part of the same cluster. This I will come later on. Focus on the core first, the red circles. These 3 points by default, they're a part of the same cluster. Now what happens is that, if I talk about this particular point, say this one, this is say P3. Okay, this is say P3. So this was also core, right? But this was indirectly density reachable from P1. Maybe directly density reachable from P2, but indirectly density reachable from P1. That's what we explained a couple of minutes ago. Now, how do I assign the cluster membership of this P3? What I have to say is that, is P3 directly associated to any other core point or not? That means, is P3 directly associated to, or it's directly density reachable from any other core point or not? The answer is yes, and that is P2. Getting it? Getting it? That means P3 will be a part of the cluster what P2 is also a part of. But P2 is already a part of one cluster, say let it be C1. Are you getting this idea? Maybe it's a bit complex to understand. Just try to understand. P1, P2, they are part of the same cluster. It's done. Same neighborhood. Both are core points. They're a part of the same cluster. What about P3? P3, you have to see if P3 is attached to any of the core point or not. The answer is yes. It attached to P2 directly. It's indirectly with P1, but directly with P2. That means P3 will now automatically go to that cluster where P2 is a part of. But because P2 is already a part of C1, so now this clustering actually swallow. It will eat up. It will gobble up this P3 as well. You see how the cluster expansion happens. So now this boundary will vanish. This boundary will vanish. This boundary. And P1, P2 and P3 will become a part of one particular cluster called C1. Got this? Now anything which was directly density reachable from P3, because they are already connected to P3, so whichever cluster P3 is a part of, this rest of the points will also be a part of that cluster. Make sense? So this C1, which was smaller initially, it will now directly gobble up all other points including P3 because they are directly density reachable from P3. You see the cluster expansion is happening. It's now not taking care of any size or shape. It is just arbitrarily expanding. It's just like one cell eating up the other. Now you go back to the main diagram. If you see here, they are a part of the same cluster, but because these and these are directly density reachable, so this particular cluster will expand and it will also gobble up this. Because these and these are directly density reachable and this is reachable to this, but because this was already clustered, so this will also have a swallowing up effect. It will now expand even further. Is that sense clear? Something, at least 60%. So now all these points will now be swallowed with C1. So in case you are wondering where this cluster expansion stops, that's when this non-core points come into the picture, basically. So suppose there is a non-core point, say anything, say P7, for example. It's a non-core point. Why it's a non-core point? Whenever I took that point, whenever I draw that radius, whenever I drew that circle, the number of points within that neighborhood was less than the threshold. That's why it got designated as non-core. Right? These were designated as core because in my previous step, whenever I took that point, I draw the circle, I took the number of points within that circle, the crowd actually exceeded the threshold. That's why it was a core point. Now, if it's a non-core point, I have to see whether it's directly connected to any of the core points or not. Directly connected to any of the core points or not. If it's directly connected to any of the core points, then it will get gobbled up as well. That means this cluster boundary will also disappear. This cluster boundary is also disappearing. So P7 will also be taken up by this cluster. Although it's non-core, but it will be taken up. But imagine a certain non-core point, say P8. So imagine a certain non-core point, say P8. It is directly connected to any core point or not? Maybe yes, but on this side. But on this side, not any of this on this side. But on this side it is connected. And there are no other intermediate connections between any of the core points here with any of the core points here. They are from a different region altogether. Suppose this is a non-core point, just like P7. It was a non-core point because whenever I took the point, draw the radius, draw the circle, the crowd within that was falling short of a threshold, it was a non-core point. But it's directly connected to, say, a core point here, a core point here, and a core point here. Okay. Now, if it's directly connected, say it's connected to a core point, say P9. Is P9 clustered? Let us say P9 is clustered. Let us say P9 is clustered by this. Say P9, P10, and say P11. Now, P8 will go to that cluster of its nearest core point. So out of all these three, suppose it's connected to P9 and P9 is a core point. So this cluster will now gobble up P8. But there is a disconnection because P8 from this side, it's not connected to any of the core points. You see, there is a cluster separation happening. Because you might be wondering that if this cluster keeps on ruthlessly expanding, when it's going to stop? This is the stopping criterion. That means you got to find a certain non-core point which is not connected to a certain core point from this cluster. If it's connected to any of the core points from this will also get gobbled up and these two clusters will merge up to become one. Pardon? Similar? No. This is not about similarity. This is about this density actually, the crowd. Similarity, I mean, the new density-based methods, they have similarity. Those are graph-based basically. Here there is no concept of similarity. Here like, are you lying within my neighborhood or not? That's it. Here there is, but even then, this closeness is done by Euclidean distance actually. You see, yeah, quite possible because this is very much parameter sensitive sort of. If you change the density, if you change the radius up and down, you will see the cluster configuration is getting changed. Suppose from 5 threshold, I go to 50, 90% of the points will be non-core. Are you getting this point or not? There will be very few clusters forming. So it's very, very parameter sensitive. That's the disadvantage of DB scan. Right. So there are multiple methods. Maybe today we cannot discuss it actually. So the primary reason for this cluster bifurcation is that you got to find a non-core which is not connected to at least one of the clusters which is formed. If P8 was connected to at least one of the core points from this side, both the clusters would have now merged to become one gigantic cluster. Right? But the third case is, how do you find the noise or the outliers? If non-core are also getting swallowed up, core points by default, they are already a part of a certain cluster. How do you find these points? These points, these are my outliers, right? How do you find them? So the way we find them is this explanation. And perhaps this will be the last explanation of today's session. Suppose I have an outlier, say P13. P13, not an outlier, but a non-core point. Remember, core points are never outliers. Core points, by default, they are a part of a single point cluster. If nobody takes them, they themselves are one point cluster. And because they are so strong, their gravity is so strong, they actually migrate to some of the other clusters. Non-core points, they are not clustered. They start with a non-cluster membership. If somebody is fortunate that, okay, take me as a part of your group, I'll be a part of your group. That kind of status that they enjoy. They themselves don't have any cluster membership to start with. So these are actually, mercy points at the mercy of the core points, basically. These are the core points. They themselves are a part of the clusters. They further expand. Now, suppose you take a non-core point, and it's a non-core point. That means whenever you took that point, draw the radius, draw the circle, it fall below the threshold. And it is connected to some points. And all of them are non-core as well, unfortunately. These are also non-core. Here the situation was different. This was non-core, but they had certain core points which lied within their epsilon neighborhood. This was also non-core. P7 was also non-core, but it had some points which lied within its epsilon neighborhood. That's why it went to that cluster and transitive relationship happened and it went to the bigger cluster. This also, P9 was a part of epsilon neighborhood of P8, So P8 went to P9's cluster, but because P9 was already having 3 other points, so this entire 4 points formed a cluster. But imagine a scenario where P13 is a non-core point, and in its epsilon neighborhood, there are no core points as such. They are also non-core, unfortunately. Then these points will never become a part of any cluster. They are filtered as outliers. They don't become a part of any cluster. So these are non-core noise points. These are non-core clustered points. And these are core clustered points. To sum it up, these are dense cluster points. These are non-dense cluster points. These are non-dense noise points or non-dense outlets, basically. So this is what the entire slide is all about. And with this, if you don't mind, I'd like to wrap up this talk based on the, due to the best interest of time. The time complexity is n log m. We use the range query. The data structure that we use is range query. So we pick a certain point, we fire the range query data structure to find this neighborhood. So every point has log n complexity for this range query. Because there are n number of points, it's order of n log n. Right. So the data structure we use is your KD tree or R star. KD tree, I think if you have heard about it, it's not a normal binary tree, it's called KD tree basically. So KD tree is used to store this entire structure basically. Or an R star tree, the R star tree is also used basically. So these are some of the complex definitions and all of that, so we'll not go into it. And spectral, as I said, we don't have time to discuss spectral. So yeah, thank you. With this we come to the end of this session. Yeah, thank you.